Hello, operating systems people. This is Gabriel Palmer, and this is another day in advanced operating systems. We're going to be talking again about operating system design and specifically capability-based system design, and we're going to be talking specifically about a really counterintuitive but awesome feature called memory retyping that allows us to, in a very flexible way, manage the memory of the system. So, first, let's start with some goals. And one of the overarching goals of a lot of microkernels is to make the kernel as simple as possible. As you start adding more complexity into the kernel, then inevitably you're adding policies into the kernel that make defining comparable policies at user level much more difficult. This means that you're not only expanding the size of the kernel, which is increasing the chance that there's a bug within it, but you're additionally making it more difficult to specialize the system around different requests at user level. Okay, so one of the big complexities, and this is highly non-intuitive, I think, but one of the big complexities of a lot of traditional systems is actually kernel memory management. Literally having like a kalloc call within the kernel that you use to allocate memory within the kernel, right? It's very intuitive to anybody who's programmed in C that you need malloc, right? But what I am saying is that fundamental access to malloc within the kernel is actually a huge driver of kernel complexity. And let me just throw some numbers at you. So for instance, if we look at the number of lines of code within Linux for a slab allocator, this is one of the simpler slab allocators, there are multiple in Linux, it's about 6K lines of code. It's relatively small in the grand scheme of things, but it is relatively large when we talk about the size of microkernels. And then the slab allocator is not self-sufficient. It needs a page allocator below it. The slab allocator typically asks the page allocator for contiguous spans of pages with which to use for its slabs. See the undergraduate operating system video on slab and buddy allocation for that. The page allocator itself is about 9,000 lines of code within the system. So this is getting complicated. That's a lot of code, 15,000 lines of code, right? So lines of code are, of course, an imperfect approximation of complexity, but they're a decent first-order approximation of complexity. Not perfect, but you kind of use it as an input into your judgment of complexity. And I just want to put this into perspective, right? The composite kernel is around 7,000 lines of code. So it's about the size as the entire slab allocator without, anything else that you need within a kernel. So you start thinking, okay, if the support for efficient memory allocators requires that much memory, then we might want to reconsider, right? But of course, how can you reconsider? You need malloc in the kernel, right? Again, highly unintuitive, but actually you do not. Okay, the next thing. Actually having a memory allocator within the kernel opens you up to denial of service attacks. And this is highly non-intuitive, but you might just have an application that essentially doesn't request memory, right? Because we can track memory relatively simply, but instead it asks for kernel abstractions that do a lot of memory allocation themselves. So for instance, if the kernel provides an abstraction to create a process, well, creating a process includes a lot of things. So often it'll create a thread control block, maybe a process control block. It'll require allocating a top level, a second level page table, et cetera, et cetera, et cetera, right? This is a lot of kernel memory that does not directly map just to the memory that the application is accessing, right? So this means that we might be able to create a denial of service attack on the system by asking for a lot of these kernel resources. Now you might think, and this is the proper way to think about it, well, can't we just account for all of those kernel resources and charge them in some way to the application? Well, one problem of that is that the application itself doesn't know how many resources are required. So if the application is trying to stay itself under some sort of a memory limit, it's impossible because there is a transparent layer doing a lot of that allocation. So the application does not have facilities to properly adhere to some account accounting. So additionally, if we're doing this accounting, we need to expose some sort of an API for getting that accounting information and somehow for managing it. So for instance, the Fiasco microkernel has APIs and ways to do this where we essentially can track quotas for different memory allocations for different subsystems. And it just makes the whole system more complex. And in essence, it is finding an imperfect solution to a problem. An imperfect solution is much better than no solution, and I think the Fiasco microkernel is brilliant for coming up with the abstractions that they've come up with. But if we can get away from it and create an abstraction that is actually perfect, then we should, right? Okay. So to demonstrate some of these types of attacks, you might think like, how do we do a denial of service attack? Well, create a lot of pthreads, right? Pthreads require thread control, block allocation within the kernel, and perhaps other things. Or do a fork bomb. Like I said, create a huge number of processes. Again, this is creating a lot of resources in the kernel for a relatively simple call at user level. If it's properly accounted, maybe that's okay. You'll run out of memory and fault, maybe? Again, like the failure semantics also add to the complexity of the system, what you actually do, right? So again, the core problem here is that user requests result in complex kernel allocations that are hard to track, hard to provide APIs for, hard to provide failure conditions on, and hard to put limits on. So all of this gets a little bit difficult. Not impossible, but difficult and often imperfect. Okay, so what are some options for actually doing this? If we do want to kind of track this, then we might say, let's keep it simple. Let's separate out the kernel memory from the user memory so that we kind of can allocate user memory in one way, kernel memory in another way. But the problem is then you need to decide what the ratio should be. How much kernel memory should there be to how much user memory? And that's inherently an application-specific thing. If you have something that's creating a ton of processes, well, you might need more kernel memory because there are a lot of kernel data structures. If you have a file system in the kernel, then that's a ton of kernel data structures. So that becomes hard to kind of say. So you probably instead want to have a unified pool of memory. All of the physical memory on the system could be either kernel memory or user memory, depending on how you want to allocate it, right? But this is really, really complicated because there are some features within systems that require contiguous pages allocated to be able to use those features. So there's something called huge pages or super pages. These are pages that are just huge, right? So instead of 4 kilobytes, they might be 2 megabytes or 4 megabytes or even a gigabyte, right? But it requires that all of that memory be contiguous in physical memory. So now you have this unified pool of allocatable memory. If you allocate one of the pages within one of those 1 gigabyte ranges that you want to use as a super page to map up into user memory, you might allocate it as a thread. Well, now you can't use it as a super page. So all of a sudden, this all gets really complicated. And in essence, there are just no good options here. Again, you're forced into imperfect heuristics. And if we're defining imperfect heuristics at the kernel level, then we're enforcing those imperfect heuristics above. What we'd rather do is at the kernel level define mechanisms that are very low level that allow user level to decide these types of policies in an appropriate way, right? So there are no good options when trading off between these types of things, and whatever kernel decision we make can inhibit user requirements. Instead, we would like to allow user level to define its own system and therefore its own requirements. And Fiasco is a system that has kernel level memory management, and it does all of these things that we've talked about, and it's about 35,000 lines of code. So compared again to the composite 7,000 lines of code, with lines of code as an imperfect indicator of complexity, you can kind of start to see the orders of magnitude playing out. And it's a brilliant system. They engineered their system very, very well given the design that they have. The question is there another design that does not force the kernel to make these decisions and therefore force user level to live with those decisions of the kernel? Instead, let's define decisions at user level so that we can specialize them around different systems, be it a small embedded system that has very little memory, or be it a fast, high-performance server system that has a ton of memory. Okay, so the general idea in one sentence is that we want user level to allocate kernel memory. Now, your knee-jerk reaction to this should be something like one of the following. Just not even processing the fact that that makes sense. Thinking, no. Bad programmer, don't implement that. That's horrible. User level controlling kernel. No, why would you want to do that? User level's bad. We can't trust it. The kernel is good. Therefore, the idea is horrible, right? These are all natural reactions. I think these are intuitive reactions. These are certainly the reactions I had when I read about this idea. But let's dive into it. It actually can be engineered to work if you design it correctly. Okay, so what do? First, we think about physical memory as a resource. So what that means is that physical memory is somehow either tracked in page tables and composite, but in a way that is inaccessible to user level, or in the capability tables in a system like SEL4. And then we think of this physical memory as something called untyped memory, which I'll call UTM. And untyped memory does not have many operations that you can perform on it. Certainly you cannot load and store to it. You can't really do anything except for retype it. You can retype untyped memory as either user level virtual memory, which I'll abbreviate as UVM, user virtual memory, or as kernel memory, KM. So user level virtual memory, once memory is typed, once a page has been typed into user level virtual memory, then we can actually map it into page tables in a way that is accessible to user level components, right? So user level virtual memory, cool, that's its type. It can be used by mapping it into page tables. On the other hand, kernel memory, once we have a page of memory typed into kernel memory, then all of a sudden we can use it to back kernel data structures. And that is the highly unintuitive part, right? How can user level have access to these system calls to retype memory and use that memory as kernel memory? This API must be safe. The kernel must not trust user level to maintain its own integrity in any way, shape, or form. So all of this must be safe in some way. The question is, how can we make it safe? Okay. Somehow, this kernel memory itself, when we have retyped untyped memory into kernel memory, that kernel memory, that KM, must then be used to construct the data structures of the system. And in composite, there are actually only two data structures that require this kernel memory. Resource tables, which again means either capability table nodes or page table nodes, and threads. These are essentially TCAPs as well, but again, I'm not really going into them much. These are the only abstractions provided by the kernel that require this memory. Conventionally, in the kernel, we would have to call kmalloc to allocate memory for them. Instead, we are retyping untyped memory into kernel memory and using that kernel memory to back these kernel data structures. Let's see how that can work. So again, this is essentially just saying that we have user-level management of kernel memory, and this is innovation of the SEL4 microkernel, and Composite changed it, but basically borrowed the idea. We thought, wow, that's a really brilliant idea. Let's just adopt that wholeheartedly. So if you want to read a lot about it, there are papers about it in SEL4. We essentially borrowed the implementation. Okay. So again, we want the kernel to be simple. What are the APIs for essentially, for instance, using this kernel memory or this user-level virtual memory? So when we want to perform an operation on a capability, we might execute a call like thread activate. And activate essentially says that we want to activate in a capability slot a new, in this case, thread. And we pass in a capability to that kernel memory that we have access to that we want to use to back that thread. Now that kernel memory is in the kernel. It's not accessible to user level. It cannot be, loaded and stored directly from user level, but it can be accessed from the kernel. And we're essentially saying, yeah, I just have a reference to that piece of memory I can't access. I'm a component at user level. I can't access the memory directly, but I have this capability that references it. And I want you to use that memory that I'm referring to through this capability to now construct a thread control block that we can then use to actually execute threads within the system. Correspondingly, if we have a piece of memory that has been typed as user-level virtual memory, we can pass in its capability, which is essentially just an address, and map it up into a page table. So that allows us to actually create memory accessible from components. So very simple APIs to actually use these pieces of kernel and user-level virtual memory. And when we're using these APIs and when we're retyping the memory, what we are trying to do is adhere to a guarantee, a very simple but important and necessary guarantee for the integrity of the kernel itself, that no memory can be used as more than one type of memory at any point in time. So if it's kernel memory, it can only be used in reference as kernel memory. If it's user-level virtual memory, it can only be used in reference as user-level virtual memory. If it's untyped, it can only be used in reference as untyped memory. And as you see, each of these types of memory have different operations that can act on them in ways that are specific to that functionality of that type of memory. So, what this essentially means is that user level cannot load and store directly to kernel data structures, right? So this is an intuitive form of isolation. The kernel data structure should not be accessible from user level. Well, that's essentially saying that memory that is typed as kernel memory cannot be mapped because the map operation can only operate on user-level virtual memory. So we just need to ensure, again, that no memory can be used as more than one type. If it's kernel memory, it can only be used as kernel memory, not as user virtual memory. Okay. This is essentially a complex state machine that encodes a lot of that intuition in how we actually implement it. In the center, we can see that we have a page that is typed as untyped memory, right? And let's follow this path. So with this path, what we can see is that we can call the retype operation where we're trying to oops, I actually mislabeled that. It's supposed to be retype to UVM, to user-level virtual memory, right? And we're essentially kind of taking user-level untyped memory, retyping it into user-level virtual memory, and essentially saying, okay, now it's user-level virtual memory, and let's imagine that we have a reference count associated with it. We, of course, initialize that to 0. Now that we have memory as user-level virtual memory, we can now do additional operations that can only act on that user-level virtual memory. We can map it and we can unmap it from specific page tables. As we saw in the previous lecture, we can only do this to page tables that we have access to in our own capability table as nested resource tables. And of course, as we map it, we're increasing the reference count. As we unmap it, we're decreasing the reference count. We're seeing how many times it's mapped into user level. If it's mapped more than once, then of course we have shared memory. And then we call the retype to untyped memory, again, reverse kind of those, the retype calls on the top and the bottom. So on the bottom, it should read that we're retyping to untyped memory, right? And we pass in that user level virtual memory, the capability to it, and we're allowed to retype from user level virtual memory essentially only if the reference count associated with that memory is 0, which is to say that we know that it's no longer mapped into any user level mappings. So if it's no longer accessible to user level, then we can convert it back into untyped memory. Okay, Once it is untyped memory, then we can retype it to kernel memory if we choose to, right? And once it's kernel memory, again, we keep a reference count. Say the reference count now is, again, initialized to 0. Then we can start using it as specific kernel data structures. So for instance, we can do a cap table activate to actually activate that kernel memory as a specific data structure within the kernel, that of a capability table node. I don't have an exhaustive list of these activate calls here. There's one for page tables as well, for tcaps, etc. But if we take that kernel memory and then activate it as a capability table, one, we increase its reference count, and now it can actually be used in the kernel as a capability table. So this is how we create kernel capability table data structures. And then after we're done using it as a capability table, for instance, we want to destroy the component that it was part of, then we can call cap table deactivate, which will again kind of take that kernel memory and make it not dedicated to be part of a capability table anymore, and more so be part of a just piece of raw kernel memory. And at that point, we could go and retype to untyped memory. And again, we can only do that if it's not used in a kernel data structure, i.e. if the reference count is 0. So you can see there's this life cycle of memory, and there's just a set of system calls by retyping memory that we already have access to in our resource tables into different types of memory, and then operating on that memory using the APIs that again are just operating on the resources we have access to in our resource tables. So this is effectively how we get away from having kernel memory allocation. No kmalloc, no malloc. Instead, we have untyped memory that we have access to in our page table or in our resource tables. We can retype it, and then we can keep using those resources just using the APIs of the kernel. So we're essentially kind of telling the kernel which memory to use as part of its data structures, instead of the kernel just kind of making a call to ask which memory to use. User level is in charge of that process. Of course, not every single component is going to have access to all of untyped memory in the system. So you can only essentially use that untyped memory that you have access to. You can only actually activate kernel resources when you have access to nested resource tables and are usually a capability table or a memory capability manager or a memory manager, for instance. Okay, so let's go a little bit further into what it might look like to create a kernel data structure. And I actually want to go into a little bit of detail here because it gets a little complicated with resource tables. So I'm going to go through this example where we are actually constructing a linked data structure, which is a data structure that has kind of links between different nodes within it, using user level APIs and the capabilities that we for resources that we have access to. So what we want to do is construct kernel data structures safely from user level. We're going to construct a page table that is a multi-level radix trie in a safe way, right? Okay, so on the right, we see that we have our own capability table, and at capability 1, at the offset into our capability table of cap 1, we have a reference to a page table. And what we're essentially doing is this call on the left is activating that page table node within our system. The third argument to page table activate in this example is the level of that kernel data structure that we want to create. So we're essentially saying here, I want to activate a new page table, i.e. I want to create a new page table node. I want to create it at capability 1 within my capability table. I want to use the kernel memory, not shown here in the diagram on the right, at KM1 to back that new page table node. And I want it to be a page table at the top of the page table, i.e. at level 1, right? Okay, that's fine. But we want to create a page table on a 32-bit system which has 2 levels. So we need to now create another page table node. In this case, we're going to create it at capability 2, somewhat arbitrarily, and we're going to use a separate piece of memory that has been typed as kernel memory. So this is again within our resource table somewhere. It's not shown here because it's actually in our page table somewhere. And we're saying we want to use that to back this now second level within the page table. And then the third call that we want to make is a new call, a new operation that we can perform on a page table node that we haven't gone over yet, and that is to construct, to const a linked data structure. And what this is essentially saying is that we want to hook that second level page table node referenced by capability 2 into the top level page table referenced by capability table 1 at the address ADDR, right? So you can see where that is in the capability table. So because in the page table, sorry. So because this is a page table, we can kind of say, there's an address that is used to translate through the entire page table. And that's what denotes essentially which offset into that top level of the page table we're hooking into. So this is essentially how we actually construct linked data structures in the system, by kind of using things like the const operation on page tables or capability tables to hook the second level of those resource tables into the top level at a certain address. And now we could actually use that page level that we've constructed and create a new component and actually use that page table to back that new component. This is indeed how we actually create new components in the system, by doing a whole bunch of retyping, then activations, then construction, etc. What this means is that we actually have facilities now to safely, at user level, manage the kernel level data structures. The kernel only allows you to construct 2 linked nodes when the kernel knows that you're constructing 2 nodes that are of the proper type, at the proper level, etc. So the kernel does all the safety checking for that, and it's up to user level to use that call correctly, right? This is not, again, something that any component can do in the system. For the kernel to do this type of operation, it requires untyped memory that it can retype into kernel-type memory, and then it has access to capability tables that it can activate into, and then it can actually it has access to multiple levels of these page tables, for instance, that it can then const together. So it requires a lot, and this is typically only the purview of, again, the capability managers and the memory managers of the system. So most components don't need to worry about this complexity, but some components, the constructors, the capability table managers, absolutely need to worry about it. Now you can imagine going through all these operations of retyping memory, then activating all of these nodes, then consing them together is really, really hard to get right. So for these low-level components that are interacting directly with the kernel, it needs to have libraries. The kernel API itself is very adversarial, very hard to use. So we need to have libraries that can be used to actually do a lot of this intelligence for us. So the cost kernel API is the lowest level API within the system that is effectively kind of a proxy for the kernel syscall layer, and it hides the details of doing all of the memory retyping and the activation and constructing resource tables. So what you do using cost kernel API is just ask it to map more memory or map more capabilities into page tables or capability tables. You don't necessarily tell it to, do all the retyping and all of the cons. It has all of that logic. It abstracts all of that from you. And the composite runtime library, the CRT, abstracts capabilities itself. It provides only the abstraction of components, synchronous invocations, threads, etc., and allows you to do operations directly on them. So it is absolutely necessary to simplify the system to a very, very high degree, and that is what we do using these 2 techniques. One, not exposing these types of functionalities to almost all components in the system. And then for those components that actually need to do these types of operations, ensuring that we have libraries to try to abstract out the details. So this has been user level management of kernel memory, which is a really non-intuitive operation that hopefully now you have a much better grasp of. It's really cool. I hope you enjoyed this. I will see you soon. Thank you very much.